Hey, Global Impact students. It's Mr. Ellinger. This lesson is on probability. Our learning target is to find the probability of an event using theoretical, experimental, and simulation methods. Essential understanding for the lesson: the probability P of an event is a number such that P is between 0 and 1 inclusive. Okay, our probability can equal 0, probability can equal 1. The probability of an impossible event is 0. So just to kind of elaborate on the possibilities here, the probability of an impossible event is 0, like I just said, or 0%. Probabilities can be expressed as a fraction or a ratio, a decimal, or a percentage. And depending on what we're doing, sometimes the decimal is more useful, sometimes the fraction or the ratio is more useful, and sometimes the percentage is more useful. A lot of times when we're just communicating how likely is something to happen, the percentage makes more sense because we're just used to, out of 100, okay, out of 100, out of 100. The percentage a lot of times is a useful, at least a useful form for our answers. So the probability of a certain event is 1. Otherwise, the probability of an event is a number between 0 and 1, or a percentage between 0% and 100%. When you gather data from observations, you can calculate what's called an experimental probability. Each observation is an experiment or a trial. So in an experimental probability, we don't think about what could happen. We just solely base our probability off of what we observe from an experiment or a simulation or some type of a calculation, okay? So an experimental probability of an event, this is notation, a capital P, and it's italicized in our text and whatnot, so you'll see the italicized P, but for in your writing, just put a capital P, and then in parentheses, the event, whatever the event is, okay? And a lot of times we call this a favorable event or a favorable outcome. What we're looking for the probability of. And the way that we calculate it is the number of times the event occurs, and sometimes you'll hear this referred to as favorable outcomes, over the number of trials or the number of total possible outcomes. So an example here, we have a softball player that got a hit in 20 of her last 50 times at bat. What is the experimental probability that she will get a hit in her next at bat? Well, we could look at, what's called a theoretical probability and think about, oh, okay, well, I think it's 1 out of 2 because she could either get a hit or not. Well, that's not what we're doing here. We're looking at based on past observations, and this is the past observation right here. 20 of her last 50 times at bat, she got a hit. So the probability that she'll get a hit, we're going to look at, well, how many times has she gotten hit in the past of observed number of times the event has occurred, and that's 20. What's the total number of trials? In this case, it'd be the total number of at-bats. So it's 20 over 50, which reduces down to 2 over 5, which we can convert to a decimal, which we can convert to a percent. So like I said, I believe if we were communicating to somebody, the 40% would probably be the most useful form of this probability. We would say, she has a 40% chance of getting a hit in her next at-bat. And again, it's called an experimental probability based on solely on observation. All right, so the other type of probability that we're going to look at is what's called a theoretical probability. And in a theoretical probability, we have to consider all the possible outcomes to an experiment or an activity, and that's called a sample space. We need to know the sample space before we can calculate a probability. Some basic sample spaces, like if you're rolling a die, a standard 6-sided die, there are 6 outcomes, and the sample space would be rolling a 1, rolling a 2, rolling a 3, rolling a 4, rolling a 5, or rolling a 6. Flipping a coin, 2 items in the sample space, or you could either have heads or tails, okay? When each outcome in a sample space has the same chance of occurring, the outcomes are what we call equally likely outcomes, and most of the theoretical probability that we'll do, we'll look at equally likely outcomes. Like I said, there's your example for standard number cube. We call it a standard number cube or a die. So we can calculate theoretical probabilities as a ratio of outcomes. So if a sample space has n equally likely outcomes and an event A occurs in m of these outcomes, then the theoretical probability of an event A is probability A, get notation, equals m over n. Here's a little Venn diagram just to kind of show you. The sample space would be the outer circle. all the total outcomes. And however many are in this inner circle, those are our favorable outcomes, or the outcomes that we're trying to find the probability of. So problem A says, what is the theoretical probability of getting a sum that is an odd number on one roll of 2 standard number cubes? So we are rolling 2 dice here. So we have to be very careful of the wording here. We're going to take 2 dice and we're going to roll them at the same time. We want to know what the probability of getting a sum, meaning we're going to take the 2 numbers that come up and we're going to add them together to get the sum. What's the probability that the sum is odd? Okay, so we want an odd sum. So the first question is, well, we have to know what is the sample space. Right away we know that by the fundamental counting principle, there are 6 outcomes on each die. So we know there's going to be 36 outcomes. 6 times 6. Okay, so we have to remember that fundamental counting principle in the back of our mind to at least get an idea of how many outcomes there are. Now, what is the sample space look like? Because we have to be able to count how many odd sums there are. Well, here's how we could write this out. And this might be something worth writing down somewhere, because some of the problems that you do, many of the problems that we do, a lot of the times will involve rolling 2 dice. Okay, so we could get a 1 on the first and a 1 on the second. We could get a 1 on the first and a 2 on the second. 1 on the first, 3 on the second. 1 on the first, 4 on the second. 1 on the first, 5 on the second. 1 and 6. 2 and 1. 2 and 2. And so on and so on and so on. Okay? So you could have a 2 on the first one and all those possibilities. You could have a 3 on the first one and all those possibilities. And so the question, one of the questions that's going to come is, well, is rolling a 2 then a 1 the same as rolling a 1 then a 2? Involves the same numbers, but what we have to assume here is that each die is distinguishable from the other. They could be different colors. So as you can see, if you were to write all these out, if I go in some type of order like this, and it's nice to always have a system or an order to writing out a sample space, the last outcome that I would write following this fashion would be 6 and 6. Okay, so what I notice here is that I'm trying to figure out how many odd sums are there. So I start looking at these sums. Well, 1 plus 1 is even. This is odd. This is even. This is odd. This is even. This is odd. That pattern is going to continue all the way till we get to the end. If you write out the sample space and calculate this out, we're going to find out that the answer on A is we have 18 odd sums. We have 36 outcomes. So that's 1/2. That's 50%. So you have a 50% chance of getting an odd sum when you roll 2 dice and add them together, the numbers that come up together. So part B, this kind of piggybacks on what I was just talking about. Without calculating the probability, is it more likely to get an even or an odd number on one roll of a standard number cube? Is it more likely to get an even or an odd? So if we look at one number cube, one standard die, 6 sides, what's the probability? Well, half the numbers are odd, half the numbers are even. So we would say that there's a 50% chance of that happening, right? 50% chance of getting odd, 50% chance of getting even. So what would we say? These are equally likely outcomes because each has a probability of 50%. Okay, another type of probability that we can look at here is what's called a geometric probability. So the example that I have here is a baseball example. So we have a batter strike zone, depends on the height and stance of the batter. What is the geometric probability that a baseball thrown at random within the batter strike zone, as shown in the figure below, will be a high inside strike, one of the hardest pitches to hit? Okay, so here we have the strike zone of the batter. Okay, it's over the plate down here. It's between their knees and their chest, essentially. This red rectangle here is the high inside strike that they were referring to. And they're saying that it's a very hard pitch to hit. So those of you that play baseball probably know this. What we want to do is we want to know what's the probability that a pitch that is in the strike zone is going to be inside this high inside strike area. Okay? So the way that we do a geometric probability is favorable outcome, or the event that we're looking at is a high inside strike. So we find that area, the area of this red rectangle, over the total area. So the total strike zone. That ratio is our probability. So 4 times 6, it's a 4 by 6 rectangle. The strike zone is a 17 by 22 rectangle. Simplifying that, we get 0.064. So that means for a baseball thrown at random in the batter's strike zone, the probability that will be a high inside strike is about 6.4%. Okay, so here's another example, similar example. Suppose a batter's strike zone is 15 inches by 20 inches, and the high inside strike zone is 3 inches by 5 inches. What is the probability that a baseball thrown at random within the strike zone will be a high inside strike? So we want a probability that we get a high inside strike. So we got the area of the high inside, I'll just abbreviate, over the area of the strike zone. Well, our area of our high inside area is this, 3 by 5, that's 15. The area of our strike zone is 15 by 20, that's 300. This reduces down to 1 over 20, which is 5%. Okay, so if we have these two batters, which one has a better chance of hitting the high inside strike? We could say that this first batter here has a higher likelihood that the pitcher will throw the pitch in the high strike zone area because their probability is higher. So that's a simple analysis that we could do of this situation. So again, just to recap, in this lesson we had experimental probabilities, which are based on experiments or observed instances of whatever it is that we're looking at. Okay, it's not anything theoretical at all, not what you think will happen. That's our second type, which is a theoretical probability. What do you expect to happen? What do you expect to happen before you actually do anything? And then our third type of probability is a geometric probability. We have the strike zone example here. There are other examples like dartboard. What's the probability of throwing a bullseye on a dartboard? It's a little more complex geometric probability, but it's an interesting one. What's the probability of hitting a certain area on a dartboard? Those of you that like to throw darts, again, that's called a geometric probability. So we need to be able to do all three. Have a good day, folks.